So that's what I'm going to talk to you today. It's about inspection and corruption games. Topic is tremendous, and I'm not going to review the tremendous really literature, lots of monographs. So if there is somebody dealing with this stuff and I'm not mentioning, so I'm sorry directly, because it's really just impossible to do it in a talk. In my book, which I have written with Oleg Malafeev on this topic, actually, I gave some kind of review, so I'll give you also the reference to my paper where this review can be found. What is specific in my talk is that I'm approaching this topic, these models, from the evolutionary point of view. And there is really not much done in this direction. So first of all, this is the literature. I have written several papers on this stuff, but that's really the monograph here. So this is the monograph Kolokoltsov Malafeev, where, as I say, there is really some reviews of other contribution of many books which are done here, and also a bit more detailed explanation of the main approach which I'm going to present you. And the second paper, The Evolutionary Game of Pressure, this is really some sense was my program paper, where I developed my own generalization of the theory of evolutionary games. And I will tell you shortly what's this point about this extension and what's the difference with the classical approach. And this first paper, which is cited first, is actually the paper where I applied these general methods to specific inspection corruption game, and first noted this effect of quadratic fine function or power fine function, that they really give you big difference with a linear fine function, which is used in many concrete situations. And this is the last paper which I have written with my new PhD students, who is now mostly dealing with the stuff and will hopefully take over on this topic. And so, as I said, I'm approaching with the evolutionary point of view, and according to my knowledge, there are just 3 papers which dealing with corruption inspection from the evolutionary point of view. So, Mishra, this is some I don't remember, some very elementary modeling of the whole story. A bit more developed, Zygmunt Diekmann, but they still apply this standard evolutionary approach. And in standard evolutionary approach, as you all possibly, well, I'm sure you all specialists in game theory, you know that in evolutionary approach, there are pairwise interaction. And that's what Zygmunt Diekmann are doing. They say that the agent, they hire 2 agents, they hire an inspector to check their dealings, which sounds a bit kind of strange from this point of view. So really, this pairwise interaction they really do not fit to the problems of the model. And this is paper, St. Petersburg, people mostly devoted to numeric calculation, and also there is special accent on information spreading. Okay, so this is the abstract of the story. As I mentioned already, inspection corruption games from the evolutionary point of view, and namely my general extension of the evolutionary game, pressure and resistance framework, from which I will start talking just in a couple of slides. So the main idea, there is a large pool of small players playing against a distinguished major player. So I'm directly saying the difference with evolutionary games. They have pairwise interaction, to people, animal, whatever they interact. And here they do not play against each other. No, they play against a big major player, and between themselves they somehow discuss what would be the best strategy for them. Next point, we have here two-level hierarchy. So there is local inspector, which inspect some agents who can violate the law in whatever way. And this local inspector can be corrupted. And he is further controlled by the higher authority, some government. So we assume that there is at least someone who is honestly interested in putting an end to this corruption. This is, of course, an idealization, that there is someone which in literature usually referred to as a benevolent dictator somehow, yeah, but well, if we are not assuming that somebody is really interested in putting an end to corruption, there is, of course, no way of modeling and trying to fight with this in any way. Now, some kind of mathematical novelty. Here we get natural replicator dynamics or its generalization with switching. Yeah, we have some domains where the inspector is corrupted, some domain where there are, and the dynamics is switching from one domain to another. So on the level of mathematics, there are discontinuous right-hand side of the control differential equation. And yes, that's the result which I mentioned, which I call principle of quadratic fine, which tells you really that the controlling of corruption can be effectively done using this fine function, which has some power growth, unlike the very often used linear ones. And concrete settings that we have in mind: illegal loggings, sales of products with substandard quality, tax evasion. There are, of course, others. So, first of all, I will introduce you this general framework of pressure and resistance, which I developed in this paper 17, which is somehow the main theoretical basis for what I'm doing now for this corruption games. And then I will develop you the concrete modeling linked with this two-level hierarchy, show you some results, and show some links with real-life kind of settings framework, which you can find looking at the legislation in different countries, and indicate perspective of first developments. In fact, there is a big variety of laws which you can find in different legislations. Well, interesting to compare them to see where they can be improved in any way. But there is lots of details of the rules. And the model is such that making these details does not change actually this main point. I think this main point about quadratic fine is rather robust, but all other details, they are very flexible, and there are several kind of ways of dealing, getting concrete numbers, concrete recommendation, concrete calculations. So there's quite a lot of things to be done here for various concrete realization of the general model. And so that was the plan. So now first preliminaries. As I say, I want to just introduce you this general framework of pressure and resistance. We consider the game of many small players, say N capital, and they are playing with the principal, big player I. And now each small player has some finite collection of strategies. Yeah, this can be, of course, extended, developed to the situation with an infinite number of strategies, but for my purposes here, it's sufficient to consider there are finite number of, and therefore the state of a group of small players is just collection of numbers n1 and t, where ni is the number of players adhering to the strategy I, and the total number of players, therefore n capital, is the sum of this n1 and nt. As usual in evolutionary theory, it's often much more convenient to work not with absolute number, but with fraction. So we introduce this xi, and I divided by n, so vector x of positive, non-negative numbers, summing up to 1. And so when our n is fixed, then talking about n or x is actually the same thing. Now we have the strategy of a big player, which can be specified by some number b, and b is coming from budget. So actually how much effort this big player is going to invest in his attempt to address the issues related with interaction with the small players. And we naturally can consider the game gamma n of n plus 1 players. Yeah? So it's n small players plus this one big players. And in order to define, we just have to have payoffs bx, bn. So this is a payoff to the principal I when we have distribution of small players x, budget of big player b, the collection, the number of players n, and we have rixb. These are payoff to small players. Again, they depend on the distribution, the total distribution arcs, on the budget b, and I is the strategy. Yeah? So we assume that the payoff, of course, depends only on the strategy chosen and not on the name of a player. So they are all identical. What is the dynamics? Now we can define the dynamics as a Markov chain which develops these states in the following way. We assume that each pair of players can independently come into interaction, somehow exchange their opinions. Yeah? And if one of these two is getting essentially more, then another one can copy and so switch her strategy from the strategy bringing less money to the strategy bringing more money. Well, this is a bit somehow flexibly explained. Now, more mathematically, yeah, to mathematically define the Markov chain, we of course do the following thing: we attach to each pair of agents a clock, exponential random time, which is proportional to 1 over n, well, with some coefficient compare, which is actually not relevant. Now we have this, all these pairs have their clocks, exponential, and when the first of them ring, then these two players exchange somehow they come into interaction, and the player with the smaller payoff Ri can change to the strategy J with a higher payoff with the probability proportional to the difference. And there can be different a bit variations of this model. We can assume that the exponential clocks here, instead of making probability here, we can make exponential time depending on this. So there's some variation, but they all give the same story. And now these two main results, two main general theorems, they're not at all complicated, but they somehow capture the main ideas. First one concerning the asymptotics or the limit of this Markov chain, which was just described. When n, the number of players, tends to infinity, of course, as you may expect, the limit will be given by an ordinary differential equation. Well, so we assume that arc maximum of the payoff to the big player is B star is well defined. We assume that B star converges to some number B star depending on x as n to infinity. And we assume that the function Rxb star x, vector valued, yeah, they depend on I, they are Lipschitz continuous function of their variable. Then the Markov chain, which was described above, converges weakly as n to infinity to the deterministic process defined by the following kinetic equation. So you see, this is kind of generalized replicator dynamics. So classical replicator dynamics will be, this will be sort of quadratic here. This is a bit more general form from the point of view of the equation. Now, apart from the convergence itself, we also can specify the rates of convergence. And the rates of convergence depends a bit on the, or not a bit, they just to depend on the regularity property of R. Yeah. So this is one result concerning the limit of the Markov chain. And second result, already independent on any Markov chain, just concern this game. So we see that the fixed point of the dynamics, yeah, they define approximate epsilon Nash equilibrium for this game gamma n. And again, epsilon can be of order 1 over n, or 1 over n squared, or even 1 over n alpha, depending on the regularity of R. which I'd like to stress that for this result, we already do not need even Lipschitz continuity. Yeah? So Lipschitz continuity is really needed for these differential equations to be well defined. But when we're looking at the right-hand side, when it takes value 0, then we do not need even Lipschitz continuity, just continuity is enough. So this result is a bit more robust and requires much less assumption. It makes sense even when the equation actually does not make sense.
I have a question. So this convergence to the replicator dynamics happens only if there is sufficient interactions between the agents, right? Is this the Markov chain assumption and allowing for sufficient interactions between the agents?
Well, you see, I did describe you this Markov chain. Markov chain is defined by these rules. Yeah?
Yes.
According to these rules, so these rules define your Markov chain. Yeah?
Yes.
Now, when n tends to infinity, this collection of Markov chains converge to this deterministic dynamics. Yeah?
Okay.
So, of course, this Markov chain describe you the way they do interact with each other.
Yes. Okay.
What I'm also stressing, yeah, that the second part is not linked with the dynamics or Markov chain. Yeah? This is just a statement about this game when big player receive bxbn and small players receive rixb. Yeah? So it's more general result, independent on any exchange of opinions or dynamics or anything. Yeah? Okay. Now, what I'd like to stress also here is the difference, is the somehow similarity and difference with the classical evolutionary game. In classical evolutionary games, we have pairwise interaction. Yeah, Hawk and Dove, they interact. Yeah? So the main result of the evolutionary game theory is that the Nash equilibria of this pairwise game actually corresponds to the fixed point of dynamics, replicated dynamics. What is the difference here? That we do not have at all any pairwise games, yeah? Unlike evolutionary game. So there, how can we connect fixed point replicated dynamics with Nash equilibrium if there is no pairwise game? Well, that's what is explained here. We have no pairwise game, but we have a total games of n plus 1 players. And there, the Nash equilibrium of these games, they correspond, not exactly now, yeah, because we have this one correction, but they do correspond to the fixed point of the replicated dynamics. Yeah? They correspond. So the fixed point of replicated dynamics, they give 1 over epsilon approximate Nash equilibrium. Well, there are some comments, or some of them about, I suppose, mentioned already, that they are generalization, some generalized version of standard replicated dynamics. Now, I'm also stressing that these equations, somehow they can be written somehow just from reasonable assumptions without any Markov chain. Yeah, what's written here, we see that the increase in the fraction of agent addressing adhering to the strategy GI is proportional to the number of displays, and there is a difference of the gain of the strategy I and the average. So it increases when the strategy is better than the average. It's the same idea with the replicated dynamics. Now, this replicated dynamics also can be written without any approximation. But what I'm stressing here, that I'm particularly interested really in the rates of convergence, because eventually we're interested in the finite, the game of finite number of players. And this is a question which is somehow often ignored or often really discussed. Yeah, for example, in the model like SIR, this epidemic model, well, say this calls for large enough, and in many papers, people do not care how large enough, yeah, should be the number of players in order that this approximation should be really valid. Yeah, so here for me it's very important how much n, how big should be n. Yeah, so for example, this 1 over n. So for example, assume we have just 10 players. Yeah, so 1 over n is 10% mistake. So for models like corruption, inspection, it's already not so bad. So even for 10 players somehow, yeah, this is already not such a bad approximation. I've seen in many papers discussing this corruption and related models of terrorist attack, etc. Yeah, there is papers dealing with 3, 4 players, and then they are complaining that they cannot do more. So for me, it's different. Yeah, whenever more, the better. More the better, but we have exact estimate for the difference. And so now coming to model of inspection and corruption. Again, before going to this, I will again refer to my first slide about my papers. So in this, my initial paper, I have considered several examples. There's really terrorist attack, there is inspection, corruption, and there are many other things. There are resources sharing game, there are project evaluation games. So lots of examples which can be dealt with by this approach. And even in more detail, this is explained in this book, Many Agent Games in Socio-Economic System of Springer, Nature 2019. So when I looked at these models, terrorist attack or epidemic or inspection, sometimes I was just surprised that different people just writing basically the same equation, just with different numbers. Yeah, and one calls them terrorists, another calls them inspector, another calls them corruption agent, but they really dealing with the same equation with the same mathematics. So in this paper, somehow I put all these models together on the equal footing. So I will not talk about this general model, and I will really now return to the inspection corruption setting specific. So we have now large number M, instead of previous N, now the M. This is the number of firms, of agents, and they can violate rules. It can be M agents or can be, in fact, M places. Violation can be any. So this first natural example is avoiding tax payment. Yeah, but this can be illegal wood cutting, which is very important, say, topic for, say, Russia or Brazil or many other places. Yeah, this could be providing products of not standard quality, and many other examples. So we can assume that the violation occur on several levels. Yeah, so we can just take a bit of illegal profit, just a bit more or much more. Of course, this is finite, or it can be considered as continuously distributed. Mathematics can be rather different, and in fact becomes much more complicated to come to a detailed conclusion when this change is big. But in principle, it does not change the story essential, as one can see from modeling and the analysis. Okay, so we just have R00. This is strategy refrain from web violation, so we do not try to get any illegal profit. So V will be now the number of violating agents, and V small, V by M is the fraction of violating agents. As you see, we're always trying to bring everything to fractions. Well, like in the general model, the state of the system can be described by the vector. So x0, x1, xj, where xj is a fraction of agents adhering to the level of the legal gain rj. And of course, we have sum of all this fraction is to 1, and this sum of fraction apart from 0 is the fraction of violating agents. And we have the average level of violation, which is the sum of this xj with the corresponding levels of violation. Now, what happens with an agent when the agent is detected? So if it is detected, then legal gain is supposed to be taken from the agent, and the agent has to pay the fine of FRJ. So this function is our main mechanism design. So effectively, our objective is really to think about which F should be more reasonable from the point of view of someone who is really interested in reducing this illegal activity, which F should be more effective to fight with these illegal activities. So this is our main mechanism design. So leave it for the moment as just some function F of RJ. Now we have, apart from these agents, we have some local inspector, which is given some budget, which allows to detect violation, and we have some probability P. So probability P, we assume that the inspector inspect all these places, and with the probability P, she can find the violation. Now this P, of course, depends on the budget. And we assume that this budget is given from some higher authority, some government, to these local inspectors, a budget with which they are supposed to fight the crime. We can look at it from a bit different point of view. So P, we can consider that P is a probability to find the violation under inspection, and that everybody is inspected. Or we can say that P is just the fraction of agents which are inspected. They are slightly different probability distribution, but not the difference not very essential. And the simplest way from the point of mathematics is to think that really this is a probability and not the fraction of checks. That's not a big difference, in fact. Now, one can assume, not necessarily, but you see there is again lots of here differences which can occur in the modeling. Now we can say that P is constant, for example, but also very natural to assume that if there is quite a lot of crimes, then the government invests more in fighting. Therefore, this probability, which effectively reflects the budget, will be increasing with the fraction violation. And the simplest way of increase is, of course, the linear function. And for this particular module, we assume that this is the case. So P increases with V with some coefficient beta. Now, let's see what happens with inspector. As I mentioned, we have here two hierarchies. So we have these agents which can try to get some illegal payoff, and we have inspectors which are in fact supposed to fight with this, but some of them can be corrupted. So if inspector is honest, so inspector has two strategies, being honest and corrupt. Of course, there also can be corruption on different levels. Again, there is some extension of the model here, which we are considering. Here we're looking just two strategies, honest or corrupt. So if honest, then if this inspector finds a violator, then violator is fine. That's it. Now, if inspector is corrupted, strategy C, then she does not find detected violator, but just ask for herself the part alpha Rj of the illegal gain. So therefore, the strategy of a corrupted inspector depends on this fraction alpha, which is also kind of parameter, which we can try to see what can be optimal for inspector in different situations. Now we are saying that there is authority, which is really interested in fighting both with crimes and with corruption. So what authority is doing? Authority is doing independent inspection in local areas, but on a very small scale. So effectively, A gives big budget to local inspector to deal with this problem. But sometimes, occasionally, it makes independent checks. How much of these checks they are doing? And again, there could be several assumptions. In the older versions of the model, I assume that just authority makes just one random check about the M firms. In the more refined versions, which we are working now, we assume that A just checks some fraction. This is, in fact, more natural because in all these models, it's more natural to work with fractions rather with absolute numbers. Yeah. So more natural to assume they check fraction delta. So delta is kind of investigation power of authority, like P, probability of detecting by local inspector, is an investigation power of a local inspector, and we assume that delta is much smaller than P, which is very natural. Yeah? So if delta will be equal to P, then the authority just would not need any local inspector. Yeah? Effectively doubling the work. Yeah? So the delta should be much small, but anyway, it should be sufficient, to somehow to detect both violations and corruption. And we'll see how and when this is possible. Okay, so what happens now? Again, I continue to describe the rules of the game. Yeah, A detects an agent that violates the rules, which was not detected by the local inspector. Then the agent just pays the corresponding fine, nothing changes with I. You see, again, this is some assumption. Let me say it another way. Yeah? So independent inspector makes some checking and find some violator. And this violator was not found by local inspector. And we're saying, well, then nothing happens with inspector, just this guy is fine, that's it. Again, this is again some assumption, yeah? Because in principle, we can imagine that if the authority finds some violator which was not discovered by an inspector, that this is somehow a mistake of inspector. So inspector can be somehow punished for this mistake. As we do not consider this, yeah? Because we're really looking not for mistakes of an inspector here, we're actually looking for purposefully done corruption activity. But again, there is some assumption everywhere. Yeah? All this assumption, this is really assumption, yeah? which can be called or not called. Now, if this authority A finds a violator that was previously detected by inspector who got the bribe, yeah, then again, from the point of view of this illegal agent still pays the fine. But now already the inspector is punished for corruption. How the inspector is punished? Here I'm taking the general way of punishing corrupted inspector, which is standardly assumed in the literature. There are good review 8 and J, which describe this standard way of punishing corrupted inspector, which I'm adhering here. Yeah? So first of all, this inspector loses the illegal profit, this bribe is taken away from him. Then he also pays a fine, which is a function of illegal profit. Now it's different functions. There was F small, S F capital. And moreover, it is assumed that if inspector is found of being a corrupted inspector, then he is taken away from his position with his salary W. He is putting down to the somehow reserve position with a very small salary W0, where he already has no influence on the process and cannot actually be essentially corrupted. Yeah, so there are three things happening with inspector who is found to be guilty of corruption. Well, so this is general model. We have lots of different results. I'm showing you some papers on this thing, the different conditions, there are different details, which effectively will lead, as generalized say, to the same basic conclusion that linear functions are. Yes, please. You have a question? No? Yeah. So please, if you have a question, please do interrupt me. Yeah. I'm very happy to answer directly. Since, yeah, if something is unclear. Okay, so now for the purpose of this lecture, let me simplify everything, yeah, not to overload you with very long formulas. We assume now that J is 1. I remember J is the number of levels of legal payoffs. R1, R2, and J, so consider just 1. It essentially simplifies the mathematics, not essentially changing actually the conclusion. So we have now find function, and we will assume now that find function are of the power type. Well, of course, this is the simplest way of looking at a linear, convex, concave, depending on this gamma. They're convex, concave, or linear. Now, when this J is 1, then we can find the average payoff for a violator under honest inspector and under corrupt inspector. So this is the gain under honest inspector. So what it is, you see, so inspector is finding violations probability P, and higher authority A find violations probability delta. So 1 minus P, 1 minus delta, neither one nor another find the violation. So this probability, this violating agent gets his illegal payoff R. But when he's found, and the honest inspector, he just pays the fine. So this is the probability of being found either by local inspector or by the main authority. Now, if inspector is corrupted, then agent with illegal profit pays fine only if she is found by the government, by the higher authority A. And well, he gets his R, possibly subtracted by the bribe for the corrupted inspector otherwise. And now also the generalized replicator dynamics or generalized kinetic equation. It's very simple, of course. And now we have just two strategies, violate or not violate. So it's very simple one-dimensional equation. So this is we see that this is evolution for corrupted inspector, evolution for honest inspector, and they are of course very intuitive. So if we see if the gain for corruption is positive, if the gain under corrupted inspector is positive, then the number of agents adhering to the strategy of violation increases, and so on here. And if the gain under honest inspector is positive for violator, then the number of violators increasing proportionally. So this is very standard thing. Not very complicated formula, just imagine this P also depends on V. So there's here some equation that we like to find a fixed point. And in fact, we can find this fixed point. So one is in the corruption domain, another is in honest domain. And remember, in general situation, our dynamics will be switching. So there is something is playing in corrupted domain, something. So when this V will cross the border between corruption and not corruption, then the dynamics will be changed. But here we consider, we simplify everything as much as possible here. So here we really have two basically independent domains, there will be no switching here. But in order to see where this switching can occur, we have to look at the, of course, at the income of an inspector. So what is the additional profit of an inspector if she would like to become corrupt? So you see what happens. Remember, there are three parts in the punishments and profits. So what is the profit of an inspector who is corrupted? So he gets alpha R, that's what he gets as a bribe, and this gets how much he gets. Number of bribes minus number of detected bribes, because if this bribe is detected, that this bribe is taken away from him. So this is the gain of his corrupted activity. Now minus other fines. So for each founded detected case of corruption, she pays a fine. And also, if a bribe is just one bribe is detected, then he goes down with his salary. So this is the difference with the salaries. So this is the additional payoff for corruption, and corruption is useful, profitable if this payoff is positive. So this is defined as, in fact, defined as the domain of corruption. When this is positive, this is domain of corruption. So a bit more concrete, these numbers, this average, they are easily found because it's, after all, some binomial distribution. I already mentioned this detail. If we consider not probability of finding, but the number of inspection, and there will be some hypergeometric distribution with slightly more complicated formulas. But adhering to P and delta as probabilities, we find here that the number of bribes, VPM, the number of detected bribes, delta PVM, and now the probability of corruption. So this is a general formula. Yeah, why this is the probability of corruption being detected. So where it comes from? This one minus, and this is a probability of not being detected. Yeah. So for each one will be 1 minus P delta, and this is the number of corrupted agents. So this is a formula. Now this formula a bit complicated for analysis, unpleasant, and we can use different regimes. If P delta Vm is small, we can approximate this by the first order Taylor term, and then instead of this QD, we can write P delta Vm. So in this approximation, the additional corruption payoff is like that, and this P corruption positive. So this thing, this equation, this is the domain of corruption. So you see, under this approximation, under all the simplifying assumptions, the domain of corruption does not depend on V. So we actually have two separate equations, one for corruption, one under corruption. When we just slightly change the assumption, just make it a bit more different, a bit more realistic, then this domain will depend on V, and we will really have the clear, explicitly switching dynamics, which is of course more complicated for the analysis. So anyways, we are now approaching to the result. Have not much time left, 15 minutes. Yeah, so let's see what we get out of this model. So I recall you that we are looking at the fine functions, power. So my main statement is that the fine function is linear, and this is the most inefficient way of doing things. And if it is power, and best of all quadratic, then we can control both the corruption and illegal behavior. So try to be a bit quick now. So gamma equals 0. This will be domain of corruption. And from what I would like to draw your attention, that you see this is a lower bound for R. So for linear fine, there is no upper bound for R. So if corruption is illegal behavior is positive, then for agent, it's better to take as much as possible of this illegal behavior. The better he can, the better for him. And there's no bound, no upper bound. And this is really specific case of the linear function. Exact numbers possibly not so important. Now, if gamma more than 1, if we have power function, then corruption domain becomes bounded for all other parameters. So this is the main first conclusion. Okay, then we have exact theorem, so the necessary is for corruption, again, exact bound for R when it is positive, profitable. And again, we see that R should be big. Yeah? So this linear fine function actually supports the big violations. And that's what we always often see in real situation. So which really support some big what people see. And now when quadratic thing, what happens? Now the domain becomes given by quadratic equation with respect to alpha r. So first of all, to have this going on, to have it, make it not empty, we have positive discriminant, so there is some bound for f again, but the bound for f was again previous case. But now we have that alpha r is between two numbers, two roots of the thing. We'll see directly that we have upper bound. So this is a clear sort of qualitative point in this whole thing. Again, we have exact numbers, when parameters, when this corruption happens, when the legal gain is profitable. And when I'm saying profitable, we always mean this profitability in the stable rest point of the dynamics, or actually in the Nash equilibrium. Okay, so again, this exact number, you can look at them in my papers, not so important. The main point I told you already. Okay, so again, main points which I'd like to stress of the theory. So the condition which we got here, well, there's exact numbers. Yeah? So they are very restrictive. When we have quadratic, fine, we have very restrictive bounds for the parameter, which allows the corruption in a stable equilibrium, which is completely different from linear case when no upper bound for illegal gain is present at all. Now, even if the conditions are fulfilled, which are restricted, the profit is again bounded and they have very, in fact, thin layer. So this illegal profit lie, in fact, in the thin layer around 1 over delta F, 1 over delta F. Remember, delta is a some investigation power of the authority. F are the constants defining the power function for the fine, for the agents, and for corrupted inspector. Well, let's say that illegal profit is proportional to the average fraction of the inverse of nominal fines expected by A. Numeric examples now. I have not much time. I suppose I have about 5 minutes. There's interesting discussion to relate this to real laws. Yeah? So if we take f small 1, f10, these somehow reasonable numbers. In Russia, for tax avoidance, we have linear fines with f04, 02, which is effectively very non-efficient. In UK, it is still linear, but already this f goes to 2, which makes it a bit more effective. Yeah, but as it shows my analysis, still not effective. Therefore, the fight with non-paying taxes is still not really solved properly. Now, for corruption, the story changes as F become bigger. And in fact, if you look at the Russian laws, then effectively the F is increasing. So the corruption laws of Russia, they kind of tend to be what I mentioned as quadratic fines, some approximation. Yeah, so law is not very well presented, but how it goes in the direction indicated. So now we'll see what happened. Yeah, if we'll take this FF as given. Yeah, then to be effective to fight with corruption, A has to have efficiency more than 10%, which is already quite a lot. But even if it have efficiency 1/2, which is very difficult to imagine, yeah, then this actually makes the presence of local inspector irrelevant. Yeah. Even then, equilibria, if they don't support corruption, they do support unbounded illegal profit. But now, if you consider the same numbers with quadratic fine, everything becomes somehow under control. So we have some condition ensuring absence of corruption. And if the condition are not satisfied with this, still we have that this R is bounded and it's somehow around 1 over delta. So the illegal profit and corruption, the equilibrium, they have clear bounds. Okay, so a couple of comments about the variance. So I told you that I simplified everything as much as possible. There are lots of versions. Yeah. For example, I consider P, the investigation power of inspector, to depend on the linear way. We can, in the same way, assume that the investigation power of authority also depends on V. The more V, the more they do this inspection. Yeah. Then now the domain of corruption becomes V depending on V. So we have some frontier of corruption which separates the domain of corruption, not corruption. It makes really the equation kinetic equation as switching dynamics. Now also we have this approximation with P, T, V, M small. When it is big, then for the probability of detection will be 1 minus, we can take Poisson approximation up to exponentially small terms. The probability of detecting corruption is almost 1. So this reflects the intuition that inspector may not bother much about being detected. He knows that during his period of activity, he can take so much bribes that somehow will be sufficient for his whole life. That was actually approach, if you remember, in the famous story of Count Monte Cristo. He usually uses this thing here. He wanted something from an agent and say, well, I'll give you so much money that will be sufficient for your whole life. Just do now. You lose your job, but do not care. I'll give you so much money that it will be sufficient for your life. So that was also very somehow natural thing. Here we have, unlike previously, domain of corruption was for small v. Here we have domain of corruption for higher v. So again, story changes. Also, we can include some other activity of corrupted agent. She cannot just take bribe from everybody, but just use some fraction of agents from which they take the bribes. It also changes a bit the story. Also becomes switching dynamics, changes VT, VRC, so it's quite a lot of here possible versions. As I say, I consider just one R, we can consider several R, more general and more interesting even extension, which is still in the project. We have this big project, in fact, with this inspection corruption. This is to consider the inspector which are optimizing with horizon. Not just in containment, substantial horizon. And there's also version with mean field games. Okay, thank you.